All right, so today I'm starting to cover the last part of the material. It's called the Hamilton-Jacobi equation. And what this is, it's another viewpoint on classical dynamics. So this Hamilton-Jacobi theory, right? It brings together several of the things that we already know how to do. So we know Newton's equation. Well, that's for undergrads only, right? You guys don't need it. We have Lagrangians, we have Hamiltonians, and now we have this one right here. So this has several concepts that you're familiar with already, but it's a different formulation. So going back to the beginning of the semester, we were talking about action. And for instance, here, let's say that I have time in the y-axis and the coordinate q in the x-axis. And we were having that there's an initial q right here, and there could be a final q right here. And what we want to do is say that initial q is at time is equal to 0. So this is t is equal to 0. Final q is reached at some time t. So there's different paths that can take you there. Maybe they look like this, maybe they look like this. And there's several paths that take you there. So from the least action principle of least action, we can define the action. And you guys already seen this one about 2 months ago, where we say we go from an integral over time from 0 to t of the Lagrangian that depends on some qi. The Lagrangian also depends on the time derivative of q, and this can be a function of time. So we have seen this already. We can evaluate it for all paths. So you could evaluate it for all of these guys and get an action for each of the paths that you're going through. So again, this is all review, right? Nothing new. Now, if we take the stream of the action. So what we're doing is we're figuring out what this guy is. When we get 0, right? This gives us the true path. So you minimize the action, right? And this might be the true path. The shortest path, maybe. Questions about this? All right. So let's change perspective at this point. What if, so this red one right here, right, the solid one, and call it QI classical, and this path depends on time, right? So this is the true path, the classical one, the red one. Once we have that one, let's define this new quantity, and this one is a W. It depends on the initial point, the final point, Q, and how long the path takes. And what we're doing is defining this as the action taken along the classical path. This depends on time. All right, so first thing I want to mention, this is a function of Qi initial, Qi final, so that would be this Qi, that Qi, and the total time. So it's the time from here all the way up there. Make sense? So this is time is equal to 0. This is time is equal to capital T. That capital T time is the one that this function W depends on. Now this one, the action, you guys know functionals, the definition of a functional? Function of a function, right? So here, this action is a functional on the path that you take. So this action depends on this path and is a function of a function because this path depends on time. So this is just a functional on the path. And we're saying that the action that can be on any path, but the action when it's for the classical path is our new quantity W. Questions at this point? We just defined it, right? All right, so let me move on then. Yeah?
This is the two part.
Right. You found that classical path. Now you just say that that's W.
Now, if you look at the left-hand side, it only contains the initial and final information and the time difference. What is the information of the two parts? Because
We just define it like that. So that's the definition, right? Now we want to figure out if that makes sense. So yeah, this is just its definition. So you see the true path only depends on here to here and this time distance.
so the record time, factor is kind of related to the two parts.
Yep. So this distance in time between those 2 points and the location of these 2 points. And that's it. That's all you need to define W. But then that's how you define W, right? So it's like saying like, I need an integer, and a real. That's my definition of this function that takes integer, and real, and is equal to this. So now we have to work with this side, but this is a function of A, B, and C. Takes three inputs, and now we have to figure out how do we work with those 3 inputs to get my output. If you're thinking programming wise, right? So now that's our definition that is equal to this guy. And what else do I want to say? Yeah. So now let's ask what happens Q initial is fixed, but we vary Q final, the endpoint, right? So if we go back to, I forget what chapter it was, but the one about the action, variation of the action. And we saw that when varying the action, we had the following expression to do. So this is the variation on the action. And again, you get to put the things that go here. So it's the same as this equation, right? But now I'm going to vary the things that are inside of this, the integrand, and you see that it depends on qi, qi dot, and time. So now that means that I have this one, and it's going to depend on the integral. Integrand depends on these things now because it's the variation. Partial time derivative of the other partial. Then this one right here. And then we have an extra term here that is also evaluated already at 0 and t. So what happens if I evaluate this on the classical path? Look, what happens when I evaluate this on the classical path? This first part, the thing in the bracket, the square bracket.
It should just go to 0, right?
Yep. So this one goes to 0. And what we have now is that, oops, wrong thing. So we would have that this guy, the W, when we are doing this Q with respect to the final, is equal to the other terms that are left there. So this one went to 0. So we're just left with this part right here. DL partial with QI evaluated at T is equal to time, the final time. So this portion right here is this guy. Not the, so this is the extremum, right? We're finding the extremum, but what we wanted to do is just vary the final point. So when we vary the final point, this is to get the extremum, these two things. This one is just a part of the bracket. That is not this delta variation on Q. So this is what we are varying at this point. Okay. So Vichal, what is this guy? DL over DQ dot. Right, so, and then it's evaluated at the last spot, right? So this is the conjugate momentum evaluated in the final position. All right. Awesome. Questions? Good. So now we're varying this final position. We also want to continue and vary we also want to compute this guy with respect to the final time, right? Because W depends on the final time. So we want to get this guy. So what we want to do is, let's take these guys right here. These are my paths again. And what we want to do is consider a classical path. So the solid one, it has a fixed initial condition. And then we could look at different, not exactly t, but we might consider running it for a little bit longer time because we're varying this guy, right? The final point. So we're not just going up to t, we're gonna vary along t plus delta t, lowercase t. So just move it in that direction. Maybe we're running for a little longer than before. So we start at QI initial and runs for t plus some tiny change delta t. So if we do that, if we were to do that, what I'm going to have is that I want to write this dw capital T, right? Because it depends on capital T. And this one is the partial with respect to capital T plus the partial of W with respect to Q final and here this is Q dot, right? I final, because that would be the partial with respect. So we're doing partial of W with respect to Q final, and then times the partial of Q final with respect to time. So that's just Q dot final. Make sense? You guys know all of this mechanisms already, right? So if we do that, we actually have this term stays there. But then this one, dW final, we already know what that is from before. This is my PI final, and then I have the QI final. Questions there? Now, turns out that this derivative is also easy to calculate, right? Because if I take the derivative of the action with the full derivative of the action with respect to the capital T time, what do I get? What was that? Lagrangian, exactly. So if I say this thing, I can do it really easy because this is just the Lagrangian. So let me rewrite this, dW right here with t is equal to the Lagrangian that depends on q. So I have to be careful now, right? This depends on that because it's w, it depends on the classical and the final time. It depends on this q dot classical and also final time. And all of this is the final time. And if we look at this, by definition, this is classical at the final time, right? So this is the Lagrangian that depends on qi classical at the final time. So this is our final position, right? And this is the same thing here, except the dot is there. So this is the qi final, and this is the final time. So I have now a way to get, so here we were doing this quantity, right? This one is equal to this. So this one is equal to this, and this one is also equal to the Lagrangian. So now, if I want to know what this guy by itself is, we have that the partial of W with respect to the final time is equal to negative Pi final Q dot final multiplied together minus my Lagrangian evaluated at the final time with Qi final, Q dot final, and final time just there. And what is this guy? Exactly. Negative Hamiltonian, right? And this is Q final, P final. Just a legend, we see the Legendre transform there, and then the final time. All right, so every Q that we have here is just going to be the final Q. Every time that we have here is just going to be the time capital T, right? So this is the only time. This is the only position, Qi final. So we can just say, okay, we're done with, that's the only one. We don't have to even differentiate anymore between what Qs we're talking about, what time we're talking about, and then just drop those superscripts and just call the capital T just time. So we have a function, a time-dependent function on configuration space this function is one that depends on Qi and T And this function satisfies that the partial with respect to Q I is going to be the momentum, and the partial with respect to time is going to be the negative Hamiltonian. And then we have that the Hamiltonian depends on P, Q, and time. This is just normal time. Questions? So this satisfies what you were wondering, right? Samir? We define it, it has inputs. Now we have it defined completely so that this function, whatever it is, we know that its derivatives are going to give us those things. So if we take this equation and stick it in here, no, sorry, if I take this equation and stick it in here, I'm going to get that the partial of this function with respect to time is equal to negative h, the Hamiltonian, that depends on qi, that depends on the derivative of my function with respect to qi and the time t. This is the Hamilton-Jacobi equation. Questions? No? All right, so let's now look at the philosophy of what we have done, right? We have a solution. We have shown how a solution to the Hamilton-Jacobi equation can be constructed just from classical paths. So here, this is my classical path that reach this point at a time capital T, starting from some point Qi, initial point. This starting point, Qi initial, right, is an integration constant. So whatever space you're in, if this is three-dimensional, whatever, those will be your three integration constants, right? So what we have is a way to get this equation out of this classical path. There are other solutions to the Hamilton-Jacobi equations that are related to the classical action in some way or another. The one that we found is the one that depends on our integration, on setting the reference point Qi initial as our integration constant. But you can do other ones that are built in a similar fashion. So suppose we have a solution to this guy. What do we do with it, right? We have some time-dependent function, W, that depends on Qi and T on configuration space. So if we have a solution, to the Hamilton-Jacobi equation, we have W that depends on Q and T. So this is time-dependent function on configuration space. We can combine it with Hamilton's equations, with the first Hamilton equation. And this one is Q dot I is equal to the partial of the Hamiltonian with respect to the momentum Pi, where Pi is equal to the partial of the function W with respect to Qi. So what we're doing then is that here, right? What we're saying is that we're replacing whatever PIs are, whatever conjugate momentums are, we're replacing those conjugate momentums with derivatives of a function that we know. And this is a function. So we're replacing P's with some function that depends only on Q. Okay, does that make sense? So what is this function W doing? This function W is going to tell you the path of the classical system. You started off at a point on configuration space, and W is kind of like a real valued classical wave function of your system. And this wave function is evolved following this equation right here. So you have a wave function, classical wave function, depends only on your configuration space. You started in some point in configuration space. It evolves following this equation, and you obtain the classical path of the system. Okay? So we still have one thing to do, and the question now should be, is this equation right here going to satisfy the equation of motion? So we need to prove that Hamilton's second equation this one is satisfied. And if we prove that, then we have this classical wave function of the system now. All right, so let's start with this. We have this guy is equal to the time derivative of the equation right here, right? From this equation. Start with this one. And if we want to do that, we can remove the full derivative by rewriting it as this. We have our qi, and then also have a qj right here. And then the time derivative of j plus, again, the second derivative. And now we have this partial with respect to time, partial with respect to qi. So we can rewrite it like that. And have this salad. But if we look at this one right here, the Hamilton-Jacobi equation, if we differentiate this with respect to qi, we see how to write the second term, right? So from the Hamilton-Jacobi equation, we then have that this is equal to, and then again, it's just differentiating with respect to q, this side. And we'll get Hamiltonian qi. Remember that the Hamiltonian depends on p. Qi qj, right? And what this is, because we know what this guy is right here, right? Is qi minus q dot j q I q j. So now we have that this one is sticking it back over here, right? So we have this one is this equation right here, and I could stick that one over here. And you see that things cancel out, right? Minus this one minus this one. And we have that this is equal to this. Yeah.
Can we get the second term? The second derivative w. We have a second term where we have.
Yeah, so it's this guy, right?
Yeah.
So, so I want to take derivative of this whole thing with respect to q. So I have the first term is just going to be respect to q of this, but this one depends on these things.
Oh,
So then this one is what comes out of this one, comes out of this one, but that's the p.
These are only when you're taking full derivative, right? This is just partial derivative with respect to q. So we just need that.
Right, right. So we need to do it, yeah, we need to do it like that for, no, we're just taking the derivative inside, right? So it's kind of like a Legendre transform.
Like, I was confused to the point that when we are taking a full derivative, like b by dq of w,
Right.
then of course we have to like expand it in terms of like that. But here it was just partial derivative, so I thought that we will just have one term that is minus. partial
Oh,
derivative.
yeah, no, you have to take this one and this one into account. That's what we're doing here. So that's why I have this one right here too, right? But this one is the one that gets in here. And I have to relate it to QI. So that's why I have the QI right here. To Qs, so I have the Qs, but then the Hamiltonian depends on the momentum. So that's, it's kind of like a Legendre transform. All right, so let me spend a couple of minutes talking about what we have now. We have been, so at the beginning, Lagrange equation, right? Oh, and then since we got this, we're happy, right? That's what we're after. All right, so now let's put it all together. We were at the beginning with Lagrange equations using second order differential equations of the time evolution on configuration space. So we were doing second order configuration space. Then we went to Hamilton's equations. And in Hamilton's equations, we're dealing with first order differential equations for the time evolution on phase space. So the change is this configuration space is only Qs, but you had 2 times the number of Qs that you had. Hamilton's equations took us to a PQ space, and we have first order differential equations. Both the number of equations is P's and Q's added together. So it's exactly the same thing, right? You're trading n more equations for going first order. Make sense? All right, so what do we have now? Now we have, with the Hamilton-Jacobi approach, we have n integration constants into this wave function, into this W function, and we're left with this monster right here, which is a first order differential equation on configuration space. So before, we have second order differential equation on configuration space. We went to first order equation in phase space. Now we're back to n, but now first order equations in configuration space with n integration constants. Does that make sense? How this is, the 3 match together pretty well. So you have 3 different approaches that can solve the same problem.
What is the integration constant?
Only Qs. Everything depends on Q and T. But now you have an initial integration constant that is your Q initial, right? So the Lagrangian didn't have that. The Lagrangian said you have to do second order differential equations. This guy, you just have first order differential equations, but now you have to specify the integration constants. Questions? No? So I think it's maybe something that is too abstract at this point to talk about, right? But you guys see the difference between the 3, right? Now, where are they useful? Let's get to that in the next class. How about we end here today? Unless you guys have questions. And you guys can go and enjoy the start of the long break. I'll be assigning a homework. Hopefully by the end of the day today, and it won't be due until the end of not next week, but the following week. Okay? So that we have time to discuss it.